In today's lecture, we are going to overview stoichiometry, percent yield, and introduce the concept of a limiting reactant and walk through some limiting reactant calculations. So we'll start with a little bit of a review and a walkthrough of another stoichiometry problem. And this we covered last week in class. The idea with stoichiometry, which is a big word, is that we really want to be able to predict how much we're going to make of something, kind of like predicting the amount of cookies you'll make when you are following a recipe. So we're using our recipe, which is our balanced chemical reaction, along with information about the amount of starting materials that we have, our reactants. And we use those two pieces of information together to predict our products. So the goal at the end of it usually is to predict our product in terms of mass. You can use this same technique to predict the amount of another reactant you need to use, or if you know the amount of your product, you can use it to predict the amount of reactants that were initially combined to form that product. But we're going to take a look at just the reactant to product version. When we do this, we're usually starting in units of mass with grams. And we'll use our molar mass of our reactant to convert our units of grams to moles. Whenever we convert between reactants or products within a chemical equation, we need to do that in units of moles because our reaction is a number of particles colliding with a number of particles rather than a mass reacting with a specific mass. So once we're in units of moles, then we can convert in between any reactant or product we want in our chemical reaction. In this case, we're going to go from a reactant to a product, so we're going to try to convert from moles of our reactant to moles of our product. And we're going to use that using the ratio of coefficients. And this is coming from our balanced equation. Next, we're going to need to actually report our product in the amount of product that forms in a useful set of units, and moles is hard to measure out. However, grams is easy enough. So then we'll convert into grams of our product as well. And again, anytime we're going between moles and mass or mass and moles, we're going to use the molar mass, this time of the product, for our conversion factor. And so we have the same basic steps for every single one of these stoichiometry problems. We're always going to start by balancing our equation and then calculating the molar mass of any compounds involved in the problem. If you're not sure which ones are involved, just calculate the molar mass for everything in your chemical equation. We need to do this because in these two steps, we're actually building our conversion factors that we'll use in the problem. Then the actual calculation is a three-step calculation, going from mass to moles, then our moles to moles and moles to mass, which is confusing in that we are using the same units over and over. To get around this, I always like to write out that I have a certain number of grams of an actual thing. So it's like I'm looking at 5 grams of oxygen, and I'm going to convert that into moles of oxygen using the molar mass, which is 1 mole of oxygen will weigh about 32 grams of oxygen. So then the unit is really the grams of the compound, whether it's a reactant or a product. And it's easier to track in terms of dimensional analysis in my units because my grams of oxygen will only be canceled out by grams of oxygen. And then when I'm looking at a mole ratio of coefficients, and I'm just making this up as I go here as an example, say I'm converting into water and I'll have 3 H2O moles for every 1 O2 mole, which actually probably doesn't make. So in this case, then my moles of oxygen are the unit and moles of oxygen, and they would cancel, leaving me in units of moles of water. So I would be careful and include the actual compound your unit is referring to. So that way we can utilize dimensional analysis as a guide when we're feeling a little lost. All right, so this is what we reviewed last time, and it was a lot of material to cram into a class. So let's go through another example of this carefully, so that way we're all on the same page. So this is a reaction between ammonia and oxygen, and we're trying to find out how much water will be produced. And we know that we're going to start out with 3.25 grams of ammonium. So the important piece of information here is that 3.25 grams of ammonium. We're told that we have an excess of oxygen, which means we have as much as we want. So our starting point is this 3.25 grams. So I'm going to write that down here. And notice I'm going to write that it's grams of ammonium. And I know I'm going to go through a three-step conversion because I have mass and I want to predict how much water in grams will form. And so this will follow our typical stoichiometry pattern, and I know that's going to be 3 conversion factors. And I'm going to end up in units of grams of water is my goal. So to start out, I need to build my conversion factors now that I know what I'm going to try to do. So my conversion factors come in 2 forms: balancing the equation and calculating the molar mass of my reactants and products that I'm interested in. So looking at my equation, it is not balanced. I have 2 hydrogen and I have 3 hydrogen on my reactants. So to balance those out, I'm going to multiply my water by 3. So now I have 6 hydrogen. I'm going to multiply my ammonium by 2. So now I also have 6 hydrogen. Great. Now from there, I am going to look at my nitrogen. I've got 2 nitrogen on my reactant side, so I'll multiply this by 2. So I've got 2 nitrogen on my product side. Now I'm going to look at my oxygen. I've got 2 on my reactants, and I've got 2 coming from my NO, 2 from my NO, and I have 3 from my oxygen. So I've got 5 oxygen on this side. So since I have 2 oxygen on my reactant side, I really need to have a coefficient of 5/2. This means I'm going to have to multiply my whole equation by 2, so that way my coefficients are all whole numbers. So going through and multiplying each coefficient by 2, I now have a coefficient of 4 for ammonium, 5 for oxygen, 4 for NO, and 6 for water. Okay, I have a balanced equation. Next, I need to calculate molar mass. I'm going to calculate the molar mass for anything that I actually have to work with. I'm going to start with NH3, so I need to know the molar mass of NH3. And I want to end in water, so I'm going to need to know the molar mass of water. So calculating those, my molar mass of NH3 is going to be equal to the molar mass of my nitrogen. So here's nitrogen, plus the molar mass of my hydrogen times the number of hydrogen molecules I have, which is 3. So if I add that up, I'm going to get a molar mass of 17.031 grams per mole. Now, for the molar mass of water, I'm going to do the same thing. I've got 2 hydrogens this time, so 2 times 1.008, plus I have 1 oxygen, 15.99. That's going to be a total of 18.015 grams per mole. Okay, now I have my conversion factors. I've got the molar mass of NH3, I've got the molar mass of H2O, and I have my coefficients from my balanced equation. Now I can start setting up my problem before I actually calculate it. So again, I'm starting with my 3.25 grams of ammonium right here, and I'm trying to get to grams of water. So in the spirit of not thinking too hard, I'm going to make sure that I have units of grams of H2O when I end at the top of my last conversion factor. So that way my units will be grams of water no matter what. And I know that I definitely don't want grams of ammonium to be in my final answer for units, so I'm going to make sure that is down here on my denominator, so that way no matter what, I know these are going to cancel and I won't have units that involve grams of ammonium. Now looking at my two types of conversion factors, I have grams to mole conversions with molar mass, and I have mole to mole conversions with coefficients. So I am going to use my molar mass of ammonium right here as my first conversion factor because it's the only one that has grams of NH3 in it. And this is 17.031 grams in every 1 mole of NH3. Okay, now I am in units of moles of NH3, but I don't want moles of NH3 in my final product. So I'm going to put that right away on the bottom of my next conversion factor. So that way I know that my NH3 moles will cancel out in the end. So with that, I know that I'm in moles of NH3 and I need to be in units that involve water. My molar mass will just go between the mass and moles of water, but my coefficients will allow me to convert in between moles of different reactants and products. So I'll use this conversion factor for the next step. So my moles of NH3, I just come here and I look right at the coefficient, and that is what goes in front of moles of NH3 for my units. And I want to be in units of water, so I'm going to go ahead and add that 6, that's that coefficient in front of the water, moles of H2O. Okay, now I'm in units of moles of water, which again, I don't want in my final answer, so I'm going to put it on the bottom of this third conversion factor, so that way my moles of water cancel out at the end of my calculation. And now this third conversion factor is set up for me in terms of units. It's grams of water divided by moles of water, and that is my molar mass. So 18.015 grams of water is the mass of 1 mole of water. And I now have a setup equation. I can now plug this into my calculator. I will plug in 3.25 and divide it by 17.013. I'll multiply by 6 and divide by 4, and then I'll multiply by 18.0515. And when I plug that into my calculator, I get an answer that's 5.16 grams of water. Let's remember this one because we're going to come back to this problem later, and we'll build off of it, and we'll come back and use this again. One thing we didn't get a chance to talk about last week was percent yield. Percent yield is gives the reader or your audience an idea of how effective the reaction is that you're reporting on. If you complete a reaction and only get a 10% yield, it might be the best you can do, but it does let people know that in order for planning the amount of reactants to combine, like exactly how much they should overshoot the recipe, so that way they have enough of the product they want. Percent yield is just our actual yield that we measure in lab after we complete a reaction or an experiment, divided by a theoretical yield. And that theoretical yield is the number we get or predict out of a stoichiometry problem. Sorry, stoichiometry. So this is what you can calculate. And you will always need to be given the actual yield or given the percent yield to find the actual yield. Once you have that fraction, you're going to divide it by or multiply it by 100. And note, some calculators have a percent button. We do not actually want to push that at all. You just want to multiply this by 100 to convert from a decimal to a or from a fraction to a percentage. All right, so let's look at a practice problem of this. Looking back at the combustion of octane, we could theoretically produce 15 grams of carbon dioxide when 5 grams of octane will react with oxygen. Let's say we do that reaction. We combust that 5 grams of octane, and we measure the amount of carbon dioxide. We collect it all. And it turns out we only collect 12.4 grams. We can now present the percent yield of this reaction. And it's important to note that the 5 grams of octane is not actually an important piece of this problem. So we're going to have our actual yield, or our actual mass that we determine experimentally divided by our theoretical. We're going to multiply that by 100. So that is going to be equal to our 12.4 grams we measure of our CO2 divided by the 15.0 grams we predicted by completing a stoichiometry problem, and multiply that by 100. If I plug that into my calculator, I get 82.7%. Not a bad yield. More than half. So it's as simple as that. It's really just the ratio of what you actually produce versus what you thought you were going to make. All right, now we're going to talk about limiting reactants. And this is just an extension of the stoichiometry work we've been doing. So a limiting reactant is the reactant that we have the least amount of. And normally we would just look at the two masses of our reactants and compare them and say, well, I have less mass of reactant A versus reactant B, so reactant A must limit the amount of product that forms. The problem is that every reactant is going to have a different molecular mass, and our chemical reactions depend on particles actually colliding with each other to form products. So we care about the number of molecules of A versus molecules of B when we're considering how many products form, rather than the actual mass. So we always want to compare in moles. We really want to decide which of my two reactants do I have the least amount of in terms of the actual number of moles that I have of them. But even then we aren't done, because I could have like certain amounts of moles of A and B, and it seems like one is less than the other. But I also have to take into account my coefficients, because if my coefficient is very large, like 7 for one of my reactants and it's only 1 for the other, if I have the same amount, if I have 2 moles of each, then for every 1 mole of B that reacts, I'm going to need 7 moles of A. And so I'm actually going to have way less A than B. I'll have a lot of leftover B after the end of this reaction, or an excess. And that means that A is going to be my limiting reactant, or the reactant that I have the least of, that'll allow me to predict the amount of products that form. So here's an example of this, and we'll walk through another example slower. If I want to know how much carbon dioxide is produced when I combine propane and oxygen in a combustion reaction, I'm going to have to evaluate how much I really have of both. So the big red flag in a limiting reactant problem is that you're going to be given 2 masses. So the mass of one reactant and the mass of the other reactant, right here. Well, the second I see 2 masses given in a stoichiometry problem, I know that I have to determine the limiting reactant. That this automatically becomes a comparison. And so what I do is there are a couple of ways of solving this. You can predict the amount that will form of each of your moles and how much you would need of each. But I've come to think that the easiest way to do this, especially if you get used to doing stoichiometry problems, is to just predict the amount of the product that forms, which in this case we're interested in CO2, for each of my starting amounts of my 2 reactants, and then compare those masses at the end. So if I do that, I would convert my 2 grams of octane into 0.04 moles of propane. We're not doing octane anymore. So once I have that 0.04 moles of propane, I can convert into moles of CO2 by using my coefficients. And then I can convert into the mass of CO2 using the molar mass of CO2. And I'll end up with what would be the answer to the problem, which is how much CO2 will be produced. Well, if I assume that propane is my limiting reactant, then I will produce 5.9 grams of CO2. And then I make the other assumption. I assume that oxygen is going to be my limiting reactant. I also start with 2 grams of oxygen, and if I convert this into moles using the molar mass, I'll have 0.063 moles of oxygen. So now looking at that 0.063 moles of oxygen, I can convert into moles of CO2 using my coefficients, and then I can convert into the mass of CO2 using the molar mass. And I'm going to get 1.7 grams of CO2 if oxygen is my limiting reactant. And now I compare. And 1.7 grams is less than 5.9 grams of CO2. So that means whatever reaction, whatever assumption I made that led me to calculate 1.7, that's where my limiting reactant is. And so I just backtrack from my 1.7. I go, aha, I assumed oxygen was the limiting reactant. I started with 2 grams of oxygen to calculate 1.7. So that means oxygen is the limiting reactant in this problem. And being the limiting reactant means that this predicts the amount that forms of my product. So if I do this reaction with 2 grams of propane and 2 grams of oxygen, the most CO2 I can produce is 1.7. Let's walk through another one now. Well, let's walk through one. Here is my example. All right, let's walk through this problem. So we have NH3 and oxygen forming NO and H2O. This is the same reaction we just looked at. And we had, in the previous slide, calculated how much of our water would be produced by 3.25 grams of NH3. So we already know the answer to that, right? We were able to predict the, or balance the equation. So we know we've got 4 NH3 reacting with 5 oxygen to form 4 NO and 6 H2O. And when we did our stoichiometry equation or reaction before, we had 3.25 grams of our ammonium, and we converted it into mass of water. We did that by following our 3 steps. We used 1 mole of NH3 weighs 17.031 grams to convert from mass to moles of NH3. And then we used our coefficients to convert into water, that we would use 6 moles of water for every 4 moles of NH3. And then we converted into the mass of water using the molar mass of water, which is 18.05 grams in every 1 mole of water. And that gave us 5.16 grams of water. And that's produced from our 3.25 grams of NH3. All right, so now we've also been told, though, that we have 3.5 grams of oxygen that we're limited by. So it might be that our oxygen predicts the amount of products and is our limiting reactant, or it might be the NH3. The only way to find out is to do both of is to predict the products from both of our starting materials. So to do this one, we already have a balanced equation, but we are going to need to know the molar mass of oxygen. From our previous problem, we calculated the molar mass of NH3 was 17.031 grams, and water was 18.015 grams. For oxygen, we're going to use the molar mass and calculate it from 15.999, that's the mass of each oxygen atom, times 2, which is going to be 31.998 grams per mole. So we'll use that as well as our coefficients. Okay, so let's set this up again. We're starting with 3 3.5 grams of oxygen. And we are going to need to convert this into grams of water. So my grams of water will be where I want to end up with my units. And I want to start by getting rid of my grams of oxygen. Now, my only conversion factors I have that have grams in the units are our molecular masses. So that means for these two steps, the first one and the last one, I need to use the molar mass. First oxygen and then the molar mass of water. So I'm going to go ahead and put those in. In 1 mole of oxygen, I just calculated that it will weigh 31.998 grams. And in 1 mole of water, I calculated before, it will weigh 18.015 grams. Okay, now I've got my molar masses in there. So to set up the rest of the problem and figure out my conversion factor from going from moles to moles, I know I'm going to use coefficients. And it's easy to flip those around, honestly. And so I know I want to get rid of moles of water, so it needs to cancel out with moles of water on the top half of my fraction. And to cancel out moles of oxygen, it needs to be on the bottom half of my fraction. So that way it'll cancel with the moles of oxygen on the top half of my fraction in my first conversion factor. Now that I have my units here, I'm just going to go find for moles of oxygen. I've got a coefficient of 5, so that 5 goes in front of the O2. And for water, I have a coefficient of 6, so that goes in front of the moles of H2O. I've got this set up. Now I can plug this into my calculator. I'm going to take my 3.5 grams of oxygen and divide by 31.998 grams of oxygen. I'll multiply by 6, then divide by 5, and then multiply by 18.015. When I plug that into my calculator, I get 4.2 grams of water. So my 3.5 grams of oxygen produced 4.2 grams of water. And that 4.2 grams is less than the 5.16 grams I calculated from my ammonium. So that means whatever produced 4.2 grams of water is my limiting reactant. And that came from my oxygen. So oxygen is my limiting reactant. And overall, I won't be able to produce more than 4.2 grams. This is my theoretical yield. Got another example here. This combines limiting reactants and it also incorporates percent yield. I recommend pausing the video at this point and attempting to set up this problem on your own. Maybe even run through the whole calculation. And then come back to the video and watch my solution and see where we were different. There's lots of different ways to format this. And so if you find something that works for you, please use it as long as you're able to get the correct results consistently. Okay. So in this problem, we're told that we have 4.95 grams of ethylene as a reactant. And it's going to combust with 3.25 grams of oxygen, and it'll produce carbon dioxide and water. And we want to know how many grams of CO2 are going to form. And we know that we're going to collect 5 grams at the end. All right, so let's begin. Okay, so the first thing that we need to do is balance our equation, but we don't even have an equation. So we need to figure that out on our own. We are given a very valuable piece of information that this is combusted. So we can actually write out our reaction from the information given in this problem and then balance it. So our starting materials are C2H4, that's ethylene, and oxygen. We know combustion reactions produce carbon dioxide and water, so my products are going to be CO2 plus H2O. Now that we have our chemical reaction, these are all going to be actually gases as well. We can balance it. Now I've got 2 carbon on my reactant side, so I'll put a 2 coefficient in front of my carbon dioxide. I have 4 hydrogen on my reactant side and 2 on my product side, so I'll put a 2 coefficient in front of my water as well. So now I have 4 hydrogens on my product side. Adding up my oxygen from my reactants, I'm going to have 4 oxygen from CO2 plus 2 oxygen from water to give me 6 oxygen atoms on my product side. I've got 2 on my reactant side, so if I multiply that by a coefficient of 3, I'll have 6 on my reactant side as well. All right, I've got a balanced equation. Now I can calculate my molecular weights. Again, calculating your molecular weights is molecular weights or molecular mass. You'll see it written the same way. It's just taking the sum of the molar mass of the individual atoms within the molecule. So for C2H4, I would multiply 2 times 12.01, that's the molar mass of carbon, and add it to 4 times 1.008, that's the molar mass of hydrogen. And I would get a molar mass of 28.052 grams. Now for oxygen, it's going to be 2 times 15.999. That's the molar mass of oxygen atoms individually from the periodic table. So that's going to give me a molar mass of 31.998 grams per mole. For carbon dioxide, I'm going to have 1 carbon, 12.01, plus 2 times my oxygen molar mass. That's going to give me a molar mass of 44.01 grams per mole. Put units on these other ones over here. All right, now I have molar masses as well. So now I have a molar mass of carbon dioxide. I have a molar mass of oxygen, and I have a molar mass of ethylene. And now I can go ahead and calculate the amount of carbon dioxide that forms from ethylene and then the amount of carbon dioxide that forms from oxygen and compare them. So really these limiting reactant problems require a bit more interpreting of the actual problem, but at the end of the day, it's just doing 2 stoichiometry problems instead of 1 stoichiometry problem. All right, so starting with my 4.95 grams of C2H4, I know I'm going to go through a 3-step conversion. And I'm going to end up with units of grams of CO2. Now, I know I want to get rid of my grams of C2H4 right away because that's not the units I want. And I know no matter what, I want to end up in grams of CO2 because those are the units I want. And it's my molar masses that have my actual mass to mole units in them. So I'm going to go ahead and once I place this grams of C2H4 down on the bottom of my first conversion factor, it tells me that I'm going to use the molar mass of C2H4. So in 1 mole of C2H4, I have 28.052 grams of C2H4. Same thing with the CO2. This is the molar mass if it has grams in the units. So I need to use that molar mass conversion factor. That'll be grams per mole of CO2. And in every 1 mole of CO2, I'll end up having 44.01 grams. Now to complete this and build in my last conversion factor, which is in the middle, I want my moles of C2H4 to cancel. So I'm going to put it down here on the bottom. And I'm going to want my moles of carbon dioxide to cancel. So it's going to have to go here on top. So I'll have moles C2H4 on the bottom of my conversion factor and moles of CO2 on the top of my conversion factor. So that coefficient in front of CO2 is 2, and the coefficient in front of C2H4 is nothing, so it's 1. So it'll be multiplied by 2 and divided by 1. Now that this is set up, I can plug it into my calculator. If I do that, I'm going to get 15.53 grams of carbon dioxide. That's coming from my 4.95 grams of ethylene. So I'm going to highlight that I started with ethylene and I ended with 15.53 grams. If you're like me, color coding things can help a lot when we have problems that have very similar units everywhere. A highlighter can save you a little bit of anxiety about which one it corresponds to which. All right, the next step is now starting with my oxygen. Sorry. Try to get this back. All right, here we go. Sorry for the pause. Okay. So I'm starting with 3.25 grams of oxygen. I'm going to do the same setup as before. I'm going to have 3 conversion factors, and I'm going to end up in mass of CO2 in grams. I'm going to follow my pattern I'm seeing evolve here, which is molar mass times coefficients times molar mass. So the first thing I'll do is I will set up my first conversion factor using the molar mass of oxygen. I'll have moles of O2 on top and grams of O2 on the bottom, so my grams of O2 cancel here, like that. So in 1 mole of oxygen, I have 31.998 grams. Now I want my moles of O2 out of the picture, and I want my moles of CO2 to be what I actually end up in units of. So I will take my coefficients. So in front of the oxygen, I have a 3. In front of my CO2, I have a 2. Now I have my conversion factor that comes from my coefficients. And then lastly, I'm going to multiply by the molar mass of CO2. So that way I cancel my moles of CO2 and end up with units of grams. So in 1 mole of CO2, I have 44.01 grams. Now I have this all set up and ready to plug into my calculator. I'll divide 3.25 by 31.998, multiply it by 2 and divide by 3, and then multiply by 44.01. And I'll get 2.98 grams. These are really different. So for my 3.25 grams of oxygen, I produced only 2.98 grams of CO2. So just comparing those right off the bat, this one is smaller. And that makes wherever I started with my assumption, the limiting reactant. So O2 is my limiting reactant. Now that I know how much will be produced, and the maximum amount or the theoretical amount is going to be this 2.98, I can calculate my percent yield. So my percent yield will equal my actual divided by the theoretical times 100. So that's going to be my actual yield was 5.00 grams, and my theoretical yield I calculated to be 2.98 grams. If I multiply that by 100, I get kind of a big number. I get 168%. That's large. That seems unreasonable. That seems like the type of thing that I would run back and say, I must have done something wrong. It must be 15.53. But that's not it. This is correct. And it highlights something that happens a lot in the lab. If a reaction doesn't go perfectly, there's systemic error, or if we make a little mistake, it's easy to imagine producing less than what you would expect. Like a 50% yield or a 25% yield if we really messed up. But in reality, like when we have error in our chemical reactions or side reactions that reduce the yield we would expect for our product, we can also have situations where we produce something else and we produce something that possibly weighs more, or it incorporates some of the solvent that our reactants were dissolved in, or we have some unexpected secondary reactions happening, in which case we can see yields that are larger than 100%, and it really indicates that we just don't know exactly what happened or went wrong. So when you see deviations from perfection in the chemistry lab. Note that they can give you results that are too big, and they can give you results that are too small as well. Bear that in mind. Okay, that completes the portion of our lecture on limiting reactants. Remember, we do have review slides for these chapters posted on Canvas. Going over balancing equations, the types of reactions that you need to know, and you just need to focus on double replacement or precipitation reactions, combustion reactions, and redox reactions. Our new conversions that we have using Avogadro's number, our mole to mass conversions using molar mass, mole to mole conversions using the coefficients, or sorry, the subscripts within a molecule, and our mole to mole conversions using the coefficients within a chemical reaction. And then stoichiometry, and this is our step-by-step stoichiometry guide.